So this is basic theory T102. Okay, so today we're going to be looking at 2's complement and trying to answer the following question. So, which of the following has an absolute value of the negative value of 101101111 represented in 2's complement? So what we're trying to look for here is, let's look at this in a decimal form. If I had the number minus 10, what would be the absolute value of that? Well, that's just equal to 10. So we're trying to do the same thing but in base 2, i.e. in binary. Okay, and so for this part we're going to have to learn what 2's complement is and how we can use that. So the difference between 2's complement and normal binary we can just explain down here. Well, normal binary, if we say a 2-bit number, we can go from 0, 0 to 1, 1. That's our range of values that we can use. And so you can see here that our value is going to go from 0 all the way to 3, or from 0 all the way to 2 to the n minus 1. So 2 to 2, 4, minus 1, 3. If we were using the 2's complement form, though, this kind of gives us a shift in our range of values, so we can cover both negative and positive numbers. So if we were using the same 2-bit number, 2-bit system, we would be able to cover the range from minus 2 to the n minus 1 all the way to 2 to the n minus 1 plus 1. Minus 1 in there. So let's just rub that out. Minus 1. So what you can see there is that we've still got the same range. So if I just plug in the n equals 2 here, we'll end up with from minus 2 all the way to 1. 2 to the 2 being 2 to the 1, being 2, and minus 1 being 1. And then what we can see is if we did add 2 to both these sides, we still have the same range of numbers. So we've not increased the number of digits that we can get from this binary number. We've just kind of changed the range. And what the nice thing about 2's complement is it keeps it consistent and also doesn't lose any range in the process, i.e. we don't have any duplicates encoding the same number. So how do we convert from a normal binary number to a 2's complement binary number? Well, the maximum possible value with the same number of digits as the number for 2's complement, which is to be calculated plus 1. So it's quite hard to look at what that is just in those words. So say we're using this number here, which is for 4. If we're using a 4-bit number, we can use a 5-bit number and just have a 1 at the front. So that's the maximum number of digits plus 1. So the maximum value would have been 1, 1, 1, 1, 1. And then we added 1, so that would have gone, let's just do this actually over here on the side. So we would have had the maximum number, I'll just underline this so we know what I'm doing here. The maximum value of same number of digits of the 2's complement to be calculated plus 1. So we're just going to do this down here. So in this case we're using 0, 1, 0, 0. So the maximum value that can store is 1, 1, 1, 1. And we're going to add that just to 0, 0, 0, 1. What's going to happen here is the 1 plus the 1, we're going to carry a 1 to here. 1 plus the 1, we're going to carry a 1 to here. 1 plus the 1, we're going to carry a 1 to here. So let's just do that. 1 plus 1, carry 1 is 0. 1 plus 1, carry 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. And 1, and then 0 plus 1 is then going to be 1. So you can see this is the same as the value here. The other way of doing this, 2's complement, we'll come to in a minute. So what you do is you subtract this reference value that we've just derived here from your 2's complement value here. So just use this method. So reference value minus the number that you want to have 2's complement, and you will get the output in 2's complement. So let's just double check this subtraction. So we're going to have 1, 0, 0, 0, 0 minus 0, 0, 1, 0, 0. You can see I've just extended this bottom digit by 1 just for consistency with the top. And this is quite a simple subtraction, except for when we get to this 1 here. So 0, 0, 0, 0, so we're going to have 0, 0. So when we get to this 1 here, we can't do 0 minus 1 to give us minus 1, because that doesn't exist in a binary system. So what we have to do is we actually have to look at this whole block here and say, okay, I'm taking a 1 away from this value here. So if you were looking at it in the decimal world, you'd be saying I'm taking 1 away from 4, so I should be left with 3. But what we can do is we can just say, well, we've got the 1, 0, 0. We want the biggest, what number plus 1 will give us this? So it's going to be 1, 1, 0. If we then add 1 to this, this will go this will go to 0, carry a 1, this will go to 0, carry a 1, and we'll be left with the original value. So that's the correct way to do that subtraction. You could also convert it to decimal as well, so we'd have got 4 minus 1, which is going to give us that 3 that we're looking for there. Okay, and so this is the best way to represent the negative number, which is 2's complement, and the 2's complement of the absolute value of 2's complement can be found by just converting it in the opposite way. So doing the 1, 0, 0 minus this 1, 1, 0. Another quite simple way, which we'll just come on to on the next slide, of converting just the one way is will be shown in a second. So as we mentioned, we're going to use the other more simple method of calculating the 2's complement number, and so the method of this is very simple. It's just invert the bits and then add a binary 1. So you can see that this is a lot more simple than the subtraction method on the previous slide, but the previous slide, that's a lot more of a mathematical method of calculating the 2's complement, and can be done more rigorously by computers and other such devices. So 2's complement of 0, 1, 0, 0, so that 4 we had before. And I should have mentioned on the previous slide that 4, 10, like this, all that means is 4 base 10, and base 10 is the numbers that you're used to using, so the decimal system. And 4 base 2 would be equal to 0, 1, 0, 0, i.e. in binary, base 2, because we only have 2 options. Okay, so let's calculate this 2's complement. So invert it, 0, 1, 0, 0. Well, that's quite obvious. You're going to have a 1 here, a 0 here, a 1 here, a 1 here. So that's just written here through the inversion. And then what we do is we just add the 1. So if we have our 1 added on, 0, 0, 0, 1, just for completeness. And what we're going to do is this 1 plus this 1, carry the 1, that gives us a 0. This 1 plus this 1 gives us a 0, carry the 1. 0 plus 1 is 1, 1 plus 0 is 1. 1, 1, 0, 0, this is the same as our answer. And so now what we have is our minus 4 as 2's complement. Okay. In the same way, we can reverse the operation. And what we can do is you can take the 1 away. It's kind of simple, just do the opposite. 1 is subtracted and the bits are inverted again in the opposite order. So what do we have here? Well, we have 1, 1, 0, 0, minus 1. So let's do this. Minus 0, 0, 0, 1, minus 1. And what we're going to have then is the 0 minus the 1. Well, that's going to be our minus 1 problem we had earlier. So what we can do is just kind of square these bits off. And so it's going to be 1, 0, 0 minus 0, 0, 1. So what number do we have to add 1 to? Well, that's going to be 0, 1, 1. And then the 1 minus the 0 at the front here is 1, 0, 0. So that's what we're left with here. That's correct. Then we do the inversion of these bits again. So that's 0, 1, 0, 0. And you're left with 0, 1, 0, 0, 4, which is our original value. So now what we want to do is go on to answer the question that we had on the previous slide. So we had there's 2 methods, as we mentioned, of doing this. This kind of works through, this slide works through the first method. So I'll go through this just in words, and then what we'll do is on a blank slide on the next page is invert the bits and minus 1 like we did here at the bottom. So this is the 2 methods really. So what can we see? So because we're using an 8-bit number, so we're going to have 9 bits with the 1 at the front here for the subtraction. So the maximum value of the 8-bit number plus 1 is this, and then we're going to take some value away. So we're going to have to say the outcome of this function is the value that we've been given. We want to kind of do the inverse here. We go, rather than going from the magnitude to the 2's complement number, we're going the opposite way. We've got our 2's complement number, we want to find what magnitude it has. So we can represent the absolute value as x, and then we can just substitute it into the relationship that we had before, which is the maximum digits, the maximum 8-bit value plus 1, minus our value for our absolute value for the number we're looking at as x, and then we can do the following relationship and say that the output is this, which we're given in the question. So we're trying to calculate this x. Then all we have to do is some simple algebraic rearranging, and you can see that here you've just got the x is equal to this minus this, and the output is going to be here. So this is our output. So the other way of doing it, which isn't written as explicitly, so because this is just a simple subtraction between two binary numbers, the other way of doing it is to do the inversion method and then minus 1, then the inversion method. So first of all, we take our 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, then we take away 0, 0, 0, 0, 0, 0, 0, 1. That leaves us with 1, 0, 1, 1, 0, 1, 1, 0. And then we perform an inversion. So through the inversion, we're going to be left with 0, 1, 0, 0, 1, 0, 0, 1. And let's just compare that to the previous method where we did the more thorough way, 0, 1, 0, 0, 1, 0, 0, 1. So there we have it. We've got the same answer from both methods. And so what we can see is that our answer